Okay, so back again. It's been a little while. There's been, well, I've been trying to do quite a few different things with the code, but I ended up converging on, sort of like a path forward, and I decided to code basically the autoencoder for Stable Diffusion for SDXL, which is called AutoencoderKL. So I know it's quite a bit of a jump from just a standard variational autoencoder to AutoencoderKL, but if you've been watching my video so far, I've covered every single thing that you will see in AutoencoderKL. It's ResNet blocks, it's downsampling, it's upsampling, and attention. There are some slight variations that I haven't covered before, but if you've been following along with the tensor math, then I don't want to say it shouldn't be. This is really complex stuff, and I'm making it look easy, but if you've been watching the videos thus far, you should have the knowledge, the prerequisite knowledge to follow along with what I'm doing. So let's get started. I'm gonna use the same training script that I was using last time for the variational autoencoder. I'm just going to, I'm just gonna code up this class AutoencoderKL and then just include it in the training script. The other difference is I switched the loss function up a little bit. Well, it's the same loss function, but I added another component. I added perceptual loss because that's what they're using in AutoencoderKL. So, and I'm switching the L2 norm with the L1 norm. So I'm using L1 for reconstruction, perceptual loss for reconstruction, and KL divergence for regularization. And I believe that's it. I'm not going to do a training run live because my models are getting bigger now and it's getting more expensive. So I already did a training run with this particular model. I'm just going to I'll show the results here in the video, but I'm not going to run it live because I'm trying to save my money as I don't have a job right now. And I would like to stretch that out as long as possible so I can continue working on the stuff I enjoy. So anyways, let's get started. So all right. So a few things I did. One, just using poetry now. By the way, poetry is incredible. Like, packaging used to be so hard in Python. Before poetry, it was just a nightmare. It was an absolute nightmare. And it's just so much better now. I can split my code into modular pieces and refer to the packages without having to modify the path or doing anything funky. Yeah, poetry is great. So anyways, I just created separate packages for models, and then I'm including this AutoencoderKL that I'm going to fill out right now. And then I'm just adding a model type to the config file. And, we're just going to switch on it right here. And I'm going to change this right now because I'm abbreviating things now just to make the typing more quick. So, right, using poetry, where I created separate packages for the training code and the test code, or in the model code. So the training is under a different package, and then you just have to do poetry install, and then you can run. You can run this right here. Just gonna keep that fresh. Yeah. You can run this and it will, well, once you build it, you can actually run it like this as well, as long as you're referring to the interpreter, the project interpreter. But yeah, oh, where'd it go? Yeah, here you go. Run it like this, and then, so what else did I add? Actually, let me, so, okay, yeah. So from the last video, I added pin memory. So I added some optimizations. I don't think that I had these in the last video I did. Pin memory, well, I've gone over this before, pin memory. It, from what I understand, it helps the model, it helps the operating system sets aside dedicated memory for, it doesn't allow that memory to be used for paging. So that's how I understand it. Prefetch factor, this is something that can speed up your model a little bit by repopulating data for a batch, from what I understand. To be honest, I didn't look into this too much. Let's see. I changed the saving a little bit so it doesn't save a model every time. It overwrites the best model on the local disk, and then at the very end of the training script, it writes to weights and biases. It's still not the most ideal, but it's better. It's better than it was before because it was taking up too much memory before, too much space in weights and biases. So I think that's all I added. So okay. So AutoencoderKL, basically what it's gonna look like. So you know what? Break out my iPad. So this isn't an exact replica of AutoencoderKL. It's a little bit, but it has all the essential components. I think autoencoder does a few things differently. AutoencoderKL does a few things differently, but this has all the essential components. It's not as big, it's not as large. I think there are a few more attention blocks in the original AutoencoderKL, but this is what we're gonna go with for now. So I'm just gonna draw something really quickly. Remember, our variational autoencoder basically looks like that. So now, inside one of these, so we're gonna have down encoder block. And this is going to be repeated a few times, and then we're going to go to a mid block that has attention. We'll just call it, actually we'll call it and then this is going to go to a latent bottleneck that's going to give us mu and sigma. So and then this is going to be, so mu and sigma, we're gonna, oh, this will give us z, and then we'll put z through our decoder, which is basically going to be up decoder block. And it's just going to repeat those. All the way to one, a final convolution layer, convolutional head that will output our image. That'll output our image. So the down encoder block is just going to be a ResNet block, and a convolutional downsample. So it's where stride equals 2. So input through output. A mid block is going to be a ResNet block, an attention, spatial attention, not a vision transformer, but spatial attention. And I'll show you the difference in code. It's subtle, but it's important. Oh, so it's doing this again. It's going to interrupt the whole video. Tension. Where's that block? So that's a mid block. Your latent bottleneck is just going to have conv to the where k equals 1. And that's going to give us a mu spatial, right? So it's just gonna, the difference between spatial and you know, the variational autoencoder latents that I did in my last videos, these retain the shape of an image. That's the only difference, which allows us, it gives us more expressivity. Retaining the shape of the image means that we don't have to flatten the image and send it through a linear layer, which causes a lot of problems. Exploding gradients. It's too great of a bottleneck. When we're sending it through a linear layer that goes from your flattened image to a smaller image, or to a smaller latent. And then also, I think the greater cause of problems like exploding gradients is when you go from your latent vector, and then you have to send it through a linear layer and then reshape the tensor into an image that because any noise when you're doing an upsample operation with a linear layer like that, you're propagating a lot of noise forward. I mean, it takes a little bit of noise and it really explodes it. So yeah. So yeah, spatial latents are they're the gold standard for any kind of autoencoder nowadays, or even vector quantized latents, which I haven't gone over yet, which I will at some point, probably after Stable Diffusion. I really want to get SDXL out of the way, and this is log variance. Again, it's just a spatial latent. And then a decoder block. Decoder block is just going to be upsample. This is going to be using nearest neighbor upsampling, which is pretty straightforward. And then followed by a ResNet block. Sorry, I'm writing really sloppily. ResNet block and a ResNet block. This is your up decoder block. So yeah. So yeah, this is AutoencoderKL, or at least a smaller educational version of it. But it has all the components. It has every single component that AutoencoderKL does, I believe. Or at least the essential components. So yeah, let's get started. Let's start coding this up. So, okay. Put some skeleton code here. We're just gonna debug it in this file right here. All right, I'm gonna do a top-down approach. Well, both, but I'm gonna start top-down. It's a little bit easier that way. Well, I'll build them the two most essential components. Yeah, okay, let's do top down. Let's do top down. So class autoencoder. Make sure I'm recording. Boom. All right. Also door. Channel in channels, main channels, base channels. These are going to be the basically the output channels of your intermediate layers. Latent channels are going to be 4. In channels going to be 3. So your spatial latents are going to have 4 channels. So they're going to be 4 channel images. Base channels is going to be 128. So we're going to go from 3 channels to 128 to 256 to 512. Out channels is going to be in channels, and then we're going to use group. We're going to use group normalization. So group norm is basically layer norm, but it's the same thing as layer norm except within group. So you have your channels. Like let's say you're doing group norm, the size of a group is 2, and you have 8 channels. It splits your 8 channels. It divides it by 2, so you have 4. So you have 4 groups of size 2, and it'll do layer norm basically within each of those groups. So it'll compute the normalization per group. And this is what SDXL's autoencoder uses. This is what most modern, I'd say, generative models use. It doesn't, batch norm depends on the batch, which can skew, it can skew statistics. Group norm has just been shown to be more stable. I'll probably do a video on group normalization. Maybe I'll code it up. But anyways, yeah, let's move on for now. So yeah, so we're gonna do this top down. So these classes aren't gonna exist yet, but we're just gonna code placeholders in channels. Decoder. And then the forward is basically going to do so your encoder is going to take an X and it's going to output your Z, your mu, and your log variance. And then decoder is going to output X hat. And then we're going to send X hat through a sigmoid activation function. Yeah. So let's code pass-throughs for the encoder and the decoder, just so we can get our code running. Wait, channel, channel. Okay. Okay. I think this will run in channel, right? So encoder and channels, latent channels, base channels. Takes one positional argument. Two are given. Sigmoid. Oh. Okay. 48. Expected 3, but got 1. Right, so these aren't going to work yet. Okay, all right. So they work just as pass-throughs. So now let's fill out encoder. So encoder is going to have downsampling blocks, downsampling ResNet blocks, so down blocks. Down encoder block. And this is going to go from in channel to base channel 0, and then base channel 0. So it's going to go from 3 to 128, 128, 256, 256 to 512. It's going to downsample the image and keep growing the feature channels. Okay, let's leave it there for now. Block in. Okay. This is going to have res1 going to have 2 stacked ResNet blocks and a downsample, which is why we make the stride to be equal to 2. So it learns features and it downsamples at the same time. Let's make the padding to be 1 because the kernel size is 3, so we want the same padding. So we need to make a ResNet block. Number of groups, so ResNet block 1, ResNet block 2. The parameters are in channels, out channels, and number of groups. So let's make our ResNet block class ResNet block. ResNet block. So remember, ResNet is convolution, normalization, activation, convolution, normalization, activation. Add the skip, project back in, if the channels, the in channels and out channels are different, project the original tensor back into the new space, and then add the convolved tensor to the original tensor, return it. So conv1 is nn.conv2d channel out channel. So self.skip in channels, out channel. Kernel size is just going to be 1. So it's a learnable projection. If in channel not equal out channel else, it's just going to be an identity. Kernel, so conv1 is going to be the convolutional layer, in channel to out channel, kernel size 3, padding same. So padding 1. Conv2 is going to be out channel to out channel. Right, we need self.norm1 equals group normalization. I'm just going to keep the num groups the same throughout the entirety of the autoencoder, which is 32. And out channels is going to be here. Okay, this is going to be a sigmoid linear unit, SiLU. The difference, which this is basically just f of x equals x times sigmoid x. The main thing that this activation function gives us is it's differentiable in all places. So rel u is like for some values of x, this flat line right here, it's not differentiable. There's no slope. So basically the neuron won't fire, right? The activation doesn't fire for certain values of x. SiLU solves that problem. When you multiply it by x, it makes it differentiable along the entirety of the function. So for values of x that are less than 0, that are 0 or less, it still fires, which is important because when you have these really deep networks, these deep models like Stable Diffusion or the different components of Stable Diffusion, you need to make sure, I mean, if your activations aren't differentiable for values of x that are less than 0, which it's going to happen, your neurons are literally like, your network literally isn't learning, right? It means that information from the gradients aren't being propagated to those neurons, which means your network isn't learning. And when it comes to networks, like really deep networks that need to learn a lot of subtlety, your neurons need to be firing for all values of x. So it's just, I don't know, it's just better to use, it's just better to use this function that's differentiable at all locations, or differentiable for all values of x. So place. Huh. Well, we can use it. Let's give it a space there. So doing the forward function, and then we're going to return, actually let's Hmm? Oh. So return, we're going to do age plus, we're going to project it through X. And if the channels, if the in channels and the out channels are the same, then it's just going to send it through an identity function. So that's our ResNet block. I've done this before in previous videos. I've explained it in depth. I've explained why stacking convolutional layers is better than increasing the receptivity, the receptive field of a single kernel. So ResNet. Down encoder block. Let's run this. It's supposed to be skip. Boom. 512, 64, 64. That makes sense. So we downsampled it, I think 4 times. Downsampled it 1, 2, 3 times. So it went from 512, 256, 128. Sorry, we went from 3 channels to 128, 256 to 512. And then it went from, right, the image size went from, what are we passing in? 512, yeah, to, right, it gets 3 times, so 1, 2, and then 64 is the third downsample. So where we're calling this down, in the down encoder block, we're calling this downsample operation here. Downsampling. So we're going from, this output's 128, 256, 256, 256, 128, 128, 512, 64, 64. I think I can get this done pretty quickly, so. All right. So now in the encoder, we need the middle block. This is going to be our attention. This is going to have our attention mechanism. The in channels and the out channels are going to be the same. So that's our attention block. That's our mid block, and like so let's implement this attention block. So let's see if it runs without the attention block actually. Yep. Groups. Groups. Yeah, looks like it's gonna run. Yep, same channels. Okay, so make sure still recording. Groups, channels, Q. So, okay, so the last time I implemented attention for a vision model, it was for a standard vision transformer, which attention and for the classification task, which uses patch embedding. So you extract patches from your image and then you send them through. You send each patch through a learnable linear layer, and you get these, and then you have a embedding where each index in the embedding is your image is represented by a tensor where each index is an embedding of the patch, and then you do dot product on the image with itself. This is basically going to what we're going to do in this is called spatial attention. What we're going to do here is we're going to represent the image as, so for a single pixel, you're going to have each channel in that pixel like stacked, right? So then if you flatten, so imagine you flatten your image at a pixel level, but then you keep each channel stacked for the pixel. So if you have, let's say you have three channels, each you flatten your image into a you have to reshape your image such that the pixel dimension is first, and then you have all three channels at each pixel, and then you dot product that tensor with itself. Well, sorry, the queries and the keys. You're not dot producting the image with itself. You're sending your computing the queries and keys first, and then you're reshaping the vector so that your pixels come first, and then the channels, and then you dot product it with itself. So yeah, it's similar to yeah, I don't want to say it's similar to patch embeddings. It's different. It's different. So you'll see. So oh wait, yeah, groups. I don't know why I cannot spell the word groups. Just every single time. It just, anyways. Channels. So it's just a kernel size of 1. So you're just projecting. This is, so Q is a learnable projection, right? Just like in regular transformers, like the queries, the keys, and the values are all weight matrices, right? But in this case, we're just maintaining the spatial dimensions of the image, right? So queries, keys, and values are all learnable projection, spatial projections. And then pretty sure that's it. So then def forward. Okay, so you're going to project, you're going to send X through its projection. So the query key and the value, and then the query. So first of all, let me get B, C, H, W. Okay, now we're going to reshape this tensor into B, C, H times W. Then we're going to permute 2 and 1. So now this is the result of this is going to be B, H, W, C. That's, and then this is going to stay the same. So this is going to be B, C, H, W. Oh. And then, so then we're going to multiply the query times the key. So that's going to give us a B, HW times HW. So our tension is equal to Q at K, right? And then we need to scale it. We need to divide by the square root of C. So C to the power of -1/2. So this is B, HW, HW. And so, okay, so you can see we're flattening this H times W is essentially flattening the image, right? And then we're permuting it. So you can think of this as a flattened image, right? So you have a flattened, your image is now one list, right? And then there's the stacked channel information at each index, right? So if our channels are 3, you have three pixels for each channel at each. You have three numbers at each pixel that represent the channel information, and you're going to dot product that with. So you're going to dot product that query with the key. So you can think of it as you're taking the dot product of one representation of the image on a pixel level with another representation of the image on a pixel level. So, right. And now we do, I'm going to do BMM is basically, it's similar to it, dash matrix multiplication. It's the same as doing Q at K or attention. Oh, wait, I need to do torch.softmax. Otherwise, it's not attention anymore. Softmax, attention at the pixel level. So it's going to normalize all pixels. And then I'm going to take the dot product of attention and V. And then, so that's going to give us, so right now we have the HWC. I'll leave it like this, make it easier to read. And then I'm going to do, I want to get, right, we want the output to be B, right, an image, right? We want to, we take an image in and we pass an image out. So we want HW. So to reclaim our image, we do permute 0 to 1. So this gives us B, C, HW. And then we reshape. Boom. This gives us B, C, HW. So I'm just going to put this all on one line. So, okay. Yeah, so let's run this. Num groups. Spell groups. Nope, I already fucked it up. No, it looks like it's working. Yeah, okay. Yeah, so there's our attention mechanism. There's our attention block. Oh, wait, no. Plus self dot. We always need to project it. We need to have a projection. We need the additional expressivity, the canonical expressivity of a projection. So it's just a skip connection. I mean, it's just how attention works. We need to project we need a learnable projection for X. There you go. Okay. Okay, so we have our mid block. Actually, wait, I need to do self.mid X. So X is self.mid X. So now let's see if this works. Looks like it still works. The dimensions look okay. So now we need the latent bottleneck. Let's call it LB. So bottleneck. So in channels, latent channels, super self. So these are our spatial. This is the convolution that's going to yield our spatial latent. So it's just a spatial projection. So now we're going to create our Z vector, which is just like we did in the last video, which is so Z equals mu plus epsilon times standard deviation. So we need to get the standard deviation, which is right. It's E. So log variance is exactly that. It's log sigma squared, right? Your variance is sigma squared, so log variance is log sigma squared. So to recover that, you do 0.5 times. So remember, log 2 times log of something is like, or x times log of something is the same thing as log of that thing raised to the power, right? So torch.exp. So we want to square root log variance. So 0.5, so log variance raised to the power of 0.5 is just sigma, and then you do E raised to the log, that cancels out the log, and you recover your standard deviation, your sigma. Then epsilon is, we're going to populate a vector that's the same shape of standard deviation with values from a random normal. We're going to return Z, mu, and log variance. And then X receives self dot latent C mu. Looks like it works. We should have mu and log variance now. The encoder returns. So, so the encoder. Oh, this something was wrong. Something fell off. I was like, something feels off. Okay. Yeah. So the shape of everything, or the shape of, sorry, wait, hold up. X hat. Right. So let's comment out this X hat for now because it's not really X hat, it's Z. But all the shapes do look correct. They should all be 1,4 by 64, 64 times 64. So, all right. So that's our decoder. Oh, sorry, that's our encoder. So let's do our decoder next. So the decoder is going to be up blocks, just up sample blocks, module list, up sample, or sorry, up decoder block. And it's going to be latent channel to base. Okay. So in the same way that we are going down, we're downsampling our image with the downcoder blocks with our base channels, right? 128, 256, 512. We're upsampling from 512, 256, 128. Yeah, 256, 128 channels, and then we're gonna have a convolutional head, which is the first index of our base channels list to out channels, which is going to be 3. So our decoder needs to have out channels is going to be in channels, right? Because we're reconstructing our image. So we're going to have, it's going to be 128 to 3. So we're going to intelligently combine, we're going to have a learnable spatial projection from 128 to 3, and it's going to be kernel size 3 padding 1. Oh, I'm hungry. Okay, so wait, so for block and self.up blocks, x receives block, x hat receives x, and torch in a minute. I'm doing that in the AutoencoderKL. Okay, so boom. Okay, so In channel, out channel, groups. And we're gonna do nearest neighbor upsampling. So it's gonna upsample, it's gonna scale it up by a factor of 2. And so we're gonna go from 64 to 128, 256, 512. And then the channels, sorry, that's scaling up the actual size of the image. And then mode is going to be nearest. And then it's going to be followed by 2 ResNet blocks. Oh. So, guys, if you don't use Vim, you should really learn Vim or Emacs. But coding with one of those, and then you can use the plugin in any of these modern IDEs. But Vim, I learned Vim about 13 years ago, and it really changed my entire coding practice. It's so lovely to code in Vim. Decoder. Yeah, let's run this. Let's see what we get. Yeah. Yeah, okay. I like Z there, but it's fine. Yeah, looks like that's it. The dimensions match, the input shape matches the output shape, and the latents look correct. So let's review really quickly. So let's do the 2 bottom blocks. So ResNet, we have convolution, normalization, activation. We stack those, and then we also add the skip connection as we project it. If the dimensions are different, the in channels and the out channels are different, we project it back into our output. The attention block, we have these learnable projection, Q, K, and V are all learnable projections. Then we have the final learnable projection, normalization. You know, we basically we send X through the Q and K projections, and we reshape the tensor so that we have a flattened, so you can imagine it as a flattened image with stacked channel information at each pixel index, and then you take the dot product of that, and then you take the softmax, and then you do another dot product by your values, and then you reshape it back into your original image, and then you project X. You add that to your learnable projection of X. Right? You have your mid block, which is just ResNet attention, ResNet. You have your latent bottleneck, which gives you your spatial latents. And then your encoder, and then you have your down encoder blocks, right? Which is just ResNet, and then a down sample convolution operation. All of these things which we've done before in previous videos. And then your decoder is just upsampling using nearest neighbor by a factor of 2, and then ResNet. So your encoder, downsample blocks, mid block, latent bottleneck, create your Z vector. And then you also have your you're adding your noise to the vector, your normal, your noise from a standard normal to your vector. And then your decoder is just upsample blocks followed by a convolutional head. And if we train the model, we're just gonna let it train here really quickly. Yeah, it's referencing this. I'm just calling it here. Config.latent channels. It's 4. Num groups is 32. I'll add that too. And channels are going to be 3, of course. Base channels, we've already went over that. So let's see. Summary, false. Train model, true. Save model, false. Load and test model, false. AutoencoderKL, compile, false. I also added a test run variable. So like I did in one of my other videos where I'm just, only choosing like 100 data points from the training data set to train on, just so I can verify that the model works much more quickly. So let's run this. Let's see what happens. So this is basically the exact same training code. Oh, right. So it looks like it's running. I did want to mention, I changed the loss function. So remember, it's the same, except I'm now adding in perceptual loss, which I'm using a Python package called lpip. So what perceptual loss is your, okay, so if you remember in my last video, excuse me. If you remember in my last video, I wonder if I have any screenshots of this. No. In my last video, I was trying to create less blurry images, which is it's a known problem with variational autoencoders. But I was wondering if I could at least decrease the blurriness as much as possible. I was messing around with a few different things. The reason why, so this is a known issue with variational autoencoders. One way that research has tried to solve the problem is using something called perceptual loss, which is essentially what you do is you use a pre-trained model. In my case, I'm using VGG, canonically folks like to use VGG, trained on ImageNet, but you essentially, when you compute your loss, so I'm doing a reconstruction loss, which in this case I've changed to L1 loss. Let me make sure I'm passing in L1 training test. Oh, L1, right. So I created this wrapper for the loss function, which knows what values to pass in. So it's passing in the L1 loss and the L pips loss, right? So this reconstruction loss is L1, and then the standard KL divergence that we've been doing, and then L pips, which is a package that uses a pre-trained VGG to calculate this L pips loss. So what it does is it takes your original image, your ground truth image, your label, and your reconstructed image, and it projects both of them into VGG's learned embedding space. And then it calculates the L2 norm of the images in that space. And what that does is VGG, because it's such a highly trained image model on so much data, it has really refined textures. It has really well learned textures and lines and like fine particles like hair and stuff like that. It's really good at capturing capturing stuff like that. So when you project an image to that space and then you measure a loss, it's basically saying like it can sharpen your image because it's projecting your image to a space where textures and stuff like that are modeled really well. So if your image doesn't capture that, it isn't doing a good job at capturing that, the loss will reflect that. Right, and so basically I added that term, L pips loss, to the loss function here, and then I'm multiplying it by a weight. So one issue is if this weight is too high, it'll start hallucinating because it'll start actually taking elements from the VGG embedding space. So you want to get the benefits by making sure it's not weighted too high. So it's just penalizing your images for not being sharp enough, for not having the proper texture, but it's not too high where it's actually hallucinating and including elements from the actual VGG embedding space. So yeah, it looks like our model's training, no issues. So I want to show you some results. So let's pull up. So okay, so this is our loss plot for the model that recreated these images. These look a lot. They're not perfect, right? But they look a lot better than they look more significantly more sharp than they did with the variational autoencoder that I tried. I tried adding like simple ResNet, like stack ResNet blocks and downsampling. And I had like L2 loss and standard KL divergence loss. And now I'm using Stable Diffusion XL's autoencoder. And you can see, and I'm using the perceptual loss plus the L1 norm. And you can see that the images are for sure more sharp. And here's the thing about Stable Diffusion, which is one of the things that fascinates me the most about that model, is it's okay that the reconstructed images are blurry, because the way Stable Diffusion is trained is the way it's trained is such that when you send diffused denoised latents to the variational autoencoder, it will create really sharp images. It's fascinating. I'm not going to go into that now, but these are pretty good for now. So when I actually get to putting Stable Diffusion SDXL together fully, we can revisit the autoencoder and talk about it more. But here's some of the interpolated, here's some samples from the latent space. I don't know, the stuff's really cool. Really, really cool. So yeah, the code should run either way. If I did make some kind of mistake in the code that generated those images that you just saw will be in the repo. So you'll be able to recreate it. And I mean, I basically showed you everything in this video. So there's nothing I'm missing. I'm almost positive. So, yeah, cool. Well, thanks for tuning in. Next, I'm going to start with Clip. I'm going to build Clip from the ground up. And things are starting to get interesting now. Things are starting to get interesting now. I'll do Clip and then I'll start building SDXL. Okay. Thanks for watching.